So far, we have studied the most simple case of molecular orbital diagram in which, for molecule of hydrogen, two atomic orbitals, the 1s, combine to form the sigma bonding and the sigma anti-bonding. And because each of these carry one electron, you need to place the two electrons in the sigma bonding. Alright, and you will see that for helium-2, the orbitals are the same, but you have now 4 electrons. You need to place 4 electrons in the molecular orbital diagram, placing as many in the bonding than in the anti-bonding. This is why helium-2 does not exist, because the bond order is 0. So actually molecular orbitals have a very strong predictive power even when we do not even use computers. So when you use the computer, you can actually calculate many more properties, but just on the back of an envelope kind of diagrams, we can predict stabilities of molecules and things that actually you will be able to see right here now, because we are going to make things a little bit more complicated slowly. This is not a real molecule, if you will. It is a real molecule, but not it does not present a lot of use for our everyday life. So lithium-2, what kind of molecular orbital diagram will lithium-2 have? Well, each lithium will have a full 1s and a half full 2s. So the 1s will combine with the other 1s, and notice that will form a bonding and an anti-bonding. And the same when the 2s of one lithium combines with the 2s of the other lithium, it will form another bonding and another anti-bonding. At this point, you're not able to predict why the bonding is above the anti-bonding here. It's just all related to the energy between the 1s and the 2s. But what we can say is how many electrons will be in each of the molecular orbitals that we just showed in this diagram. So in this case, each lithium, so this lithium brings 3 electrons, and this one brings 3 electrons. We need to place 6 electrons, 2, 2, and 2. Okay, so you will see that if you try to calculate the bond order for this lithium, the bond order for lithium is electrons in bonding orbitals. So we have 2 electrons in bonding here, 2 electrons in bonding here, that is 4, minus electrons in anti-bonding, meaning there's only 2 here, so 2 electrons in the anti-bonding divided by 2. This will be 1. That is, the molecule of lithium-2, has a bond order between the atoms equal to 1, a single bond. Now, how about beryllium? Notice that for beryllium, the molecular orbital should be the same. The molecular orbital diagram, as you can see, is the same. What changes is the number of electrons each beryllium brings in the combination. Each beryllium will bring, if you remember, a beryllium is a 1s2, 2s2, so each beryllium brings 4 electrons. So you need to place 2 here, 2 here, 2 here, and 2 here, right? Because you have 2 berylliums each bringing 4. That's a total of 8 electrons. So now let's calculate bond order. Bond order will give you the strength of the bond in this case, if it's a single bond, double bond, triple bond, etc., or fractional bond. Number of electrons in bonding, I have 2 here and 2 here, that is 4, minus number of electrons in anti-bonding, 2 here, and now I have 2 here also in this high anti-bonding, divided by 2, this is 0. The bond order for beryllium-2 is 0. This means that we can predict that beryllium-2 will not be stable because the bond order is 0. There is no bond. This is a simple case, a simple example of the powerful or the predictive power that molecular orbital has. The same way that we were able to predict that helium-2 did not exist because the bond order was 0, beryllium-2 does not exist either, just by filling the number of electrons on our molecular orbital diagram.